So on my flight from Europe to Xiamen in China, I had time to read a very interesting paper, which I wanted to share with you because it has very many insights which are useful to know for both computational chemists and experimentalists when they collaborate with theoreticians. This is a paper by Petr Slavicek and his group, and I should say that Petr published many interesting papers which also inspired our research. I never met him, so it's a very unbiased analysis of this publication. But he really introduced many research papers and topics which we later use ourselves too. So in this paper, what he says and his group says that even if you have the same experiment, but ask two different theoretical groups to perform analysis of the phenomena and provide a theoretical explanation of it, you can get to very different, so you will get from these two different theoreticians very different answers, which both fit to experimental observations. So you cannot judge solely on single calculations what is a correct answer. And this is pretty common, so I see it very often in my research and that I usually mention to collaborators. So here it's nice to see the paper going into details to show how it works on a real example. And the analysis is very thorough and beautiful. So here it is on the reaction of cystylbin. And so it's not the most stable isomer, so transtylbin is more stable. But if you start with cystylbin and then you do photoisomerization of it, then it either goes to more stable transtylbin, or it goes to cyclization, and then it forms this other isomer, which is higher in energy, but possible to do photochemically. And it was also observed experimentally. Now, the problem is that different experiments predict different outcomes in terms of quantum yield for these products. And as we'll see, it's a bit complicated picture there. What is interesting that analyzing stationary points of the just PS, like it usually is done, does not hint at any major discrepancy as they mention. And that's why even if you just do some calculations just on normal stationary points like minima, transition states here, conical intersections, then you can find very similar results with different methods. But when you perform later dynamics, in this case, you will get very different results. And before I proceed, so I should also say that for many of the ground state properties for small molecules, theory can provide such an accurate result that we can even rival many experimental measurements in terms of interpretation. But in case of bigger molecules, realistic settings like in chemical labs and here in photochemistry, there's still lots of work to do, and you cannot give 100% correct answer with theory. So we make hypotheses, we validate it as well as we can, but at the end, it's always just an interpretation, and we should keep this in mind. So that's natural process in science, but we should be aware of this, and then we should report appropriately our interpretations. So they were inspired also by doing some ensembles of simulations to get estimates of the sensitivity. So I will also mention later that that's a very common thing to do in machine learning, and our group contributed a lot to this. However, so this is costly, but here I would argue, okay, it depends how we do it. So we have some methods which are not that costly to get uncertainties, but it depends how we construct ensembles. So what this group means, if you construct ensembles of electronic structure methods, then of course it's very costly. But we often construct ensembles of machine learning models, as I can show later. So now the suggestion is to introduce some kind of delta correction to fast semi-empirical method and check the sensitivity. And that's very common in our research. All right, so let's dive a bit more into the paper. So first of all, it's nice that it's an open access paper, so I can just show this. So it's a CC BY license. Now, in this publication, they look at the experimental measurements and then they compiled them, and they are quite different, especially so this is equalization product, and this is this transisomerization. And I highlight here gas phase because despite all of these different experiments, experiments are also very often interpreted with the help by theory. And then it's not that in experiment you have some definite answer either. So in this case, in this gas phase, if you then read the fine print somewhere down later in the paper, it's also mentioned so that experimental gas phase quantum yields were omitted as they are not purely experimental quantities, but they are predicted on the support of the simulations with this electronic structure method. So experimental results should be also taken with a grain of salt. And if we look at all of these experiments, they were usually supported, supplemented by extensive computational studies from very, very different methods like TFT and then multi-reference wave function, semi-empirical methods, and so on. And however, so like despite all of these simulations and experimental studies, still it's not clear what's going on. And here just the emphasis that this interpretation of experimental observations really still heavily relies on theoretical support. And that will come up also later in the conclusions that if you don't have very big difference in terms of what we calculate when we try to target some observables, and if they're kind of similar to experiments, then it's very easy to accept these results. But in principle, we should test counter hypotheses because we can come up with wrong solutions. All right. And one of the things they performed, in addition to the more common surface hopping, few surface hopping schemes, they also use Landau-Zeno surface hopping. And let me just quickly show. So we were inspired by one of Peter Slavicek's work before, and that's why we also implemented this Landau-Zeno surface hopping scheme into our MLAtom package. And that will come up a bit later when I talk about one specific method based on delta learning and IIKM1, which is very relevant in light of this study. All right, so back to this paper. So they analyzed here stationary points, as mentioned in the abstract, and except for this one, which is not very, very good one, so it's so we can basically forget about that one. But the other ones pretty much agree with each other, and except for this stationary point, but in principle, if you look at the diagrams qualitatively, they are kind of similar. All right, and then when we go to the photodynamical simulations, then you see that for different methods, you get very, very different photoproduct populations as a function of time. So for OM3, which is an empirical method that's very fast, you really see that lots of trans isomers formed, but basically almost nothing or zero for cyclization product. And then here we have two other methods. And this one was not very good, so you can ignore that one. And here you can see that while this is qualitatively more or less similar, but quantitatively they're quite different for quantum yields. For CASPT2 approach, you observe lots of cyclization product, right? So it's very different from these two approaches. And very interestingly, so like if you calculate the spectra, yeah, they look, of course, not the same. And that's why you can see that these calculated spectra exhibit discernible disparities, but still they are kind of consistent trends with experimental observations. So that's why I'm saying that it's very, very hard to judge based on just theory which one is correct, because theory is always modeling an approximation to the reality. So you can get based on experiment some spectrum or whatever you measure, but theoretical results can be supporting this for the very wrong reasons. So what they did later, they put some bias potential here for ODM2 approach, and so it's here. So this is fast empirical method, and they just put very simple bias potential. This is similar to, as I also mentioned later, to the delta learning approach, and the delta learning approach is our approach which we introduced quite some time ago already, 10 years ago. And in this approach, we add the correction, machine learning correction to also some empirical methods a lot. And so I mentioned briefly AIKM1 method. So it is based on delta learning. And this AIKM1 method is semi-empirical methods plus delta learning correction based on neural networks and some dispersion. So this was published already 4 years ago. And we later also analyzed a lot the uncertainties given by this method. Because methods like AIKM1 or AIKM2, now the newer generation, they are ensembles of 8 neural networks, so you can calculate the uncertainty based on the deviation between predictions. So we usually do it on single point calculations, like here. And that's a very nice example that you can see that we see error bars for predictions with these methods, which are absent if you do, for example, DFT calculations. And you can see that usually these approaches are for ground state calculations quite kind of close to couple cluster, which is gold standard. So we exploited it when we calculated ground state properties like histoformation. And you see in graphical abstract, we put that uncertainty estimate is very important here, and that was based on ensemble. What Petr Slavicek's group referred to when they were talking about ensembles of methods, they were talking about this publication by us, so they were citing it, so saying that this ensemble provides better predictions, but it's more computationally expensive. And it is true because we combined here different DFT methods to get better accuracy. However, you can do it differently, like here, if you have neural networks as added, you can consider it as a, well, not really bias potential, but correction to the semi-empirical methods. So then you can analyze uncertainty. And so our methods, when we compared this AIKM1 approach to pure semi-empirical methods, so like pure semi-empirical methods here is ODM2, and our AIKM1 method has these neural network corrections. You see that results are discernibly different. And this is the case what Petr Slavicek also saw in his paper. So in his paper, what he saw when he had different potentials, quite different results. So basically, I completely agree with these conclusions that one can think of changing the paradigm of these approaches, like in terms of our simulations and employing these corrections to do sensitivity analysis. So like how sensitive are calculations to different changes in electronic structure methods, and semi-empirical methods plus these corrections are perfect for this because they're fast to do the simulations with, and machine learning approaches nowadays, as I showed on example of our research, provides very easy way to do this. And also, this is very important conclusion that if you have this experimental data, you can even think about fitting something to get better agreement with experimental observations. I would say that we should be careful when we do this, of course, because again, we can fit something which produces similar to experiment, but again, it can be wrong, so it can be biased, but at least that's one way to improve our results. If we do it carefully and properly, then it's a very good way to do. And in general, we should be I would not just say photodynamics community. I believe that it's more generalizable conclusion. So our computational chemistry, our experimental also community, so our community works with simulations should be in general more careful with experimental interpretation based on theoretical calculations. And one very good suggestion is basically if there are possible alternative hypotheses, then they should be suggested, right? And usually there are some alternative hypotheses. The outcome when you do the simulations should be compared, and that gives you some sensitivity analysis, how certain our results. Now, the concluding remark here is that you can also perform these calculations with emulator. So we have quite extensive tutorials, and the method that I was mentioning in AIKM1, so you can do these CI calculations with it, and you can propagate surface hopping dynamics. Here we provide tutorials, examples, so it gives here some populations. And you can also do nowadays pure machine learning simulations where we have extensive tutorials with videos, which you can find the links under the video.